A significant strength of the Raspberry Pi is its ability to interact with the environment. One of the main ways it does this is through a set of pins made available for connecting to external devices. The original A and B models had 26 of these header pins, but since 2014 every Raspberry Pi from the Model B Plus on has 40. These pins are a connection to the heart of the Pi, making the ability to pass data in and out of the device very easy, as well as providing the power required to support attached devices. Broadly speaking, there are three types of pins: a set that provides voltage that can be supplied to devices, a set that represents an earth or ground connection, and a set that is allocated for general purpose input-output. These are more commonly called GPIO pins. In fact, this entire set of pins are commonly just called GPIO header pins. For our voltage connections, there are two which can supply 3.3 volts and two which can supply 5 volts. Since the introduction of the B Plus model in 2014, the 3.3 volt pins can provide up to 500 milliamps of current via a built-in switching regulator. The 5 volt pins provide a direct connection to the 5 volts coming from the USB power being supplied to the Pi. As such, we can draw significantly more current depending on the power supply being used. Just be a little bit careful connecting these pins to other devices, since they do not have a regulator or fuse, which would otherwise provide some protection to our Pi if things went wrong. The ground pins provide a common ground or earth point for external circuits. A ground is used to complete an electrical circuit. For example, if we wanted to connect an LED, we would need to do so from one of the pins with an output voltage via our LED and a resistor to a ground pin. GPIO pins are numbered in a few different ways. It can be genuinely confusing, so it's a good idea to understand the different numbering schemes. Firstly, there's the scheme that relies on their physical location. Starting at the top left, there is a small notch in the outline around the pins that designates the location of pin 1. The pins are then numbered left to right and downwards. Physical pin numbering is the simplest way to locate a pin, but many of the tutorials written for the Raspberry Pi follow a different numbering sequence. Broadcom Pin Numbering, or BCM numbering, is also known as GPIO Pin Numbering. It is used because it is mapping the pins according to their connection to the Broadcom system on a chip that is at the heart of the Raspberry Pi. This is a scheme that at first glance looks pretty random, but it takes into account the practical connections to the system on a chip. The pin identifier will be prepended with either BCM or GPIO and then the appropriate number. Any of the GPIO pins can be configured in software to receive an input or to produce an output. If it's reading an input, the pin will read a high as a voltage of 3.3 volts and a low as 0 volts. If it's generating an output, it will produce 3.3 volts to represent a high and 0 volts to represent a low. When producing an output, the maximum amount of current that can be drawn from a GPIO pin is only 16 milliamps. That's not a lot. With that much current, we could light one, maybe two LEDs, but that would be it. Most of the GPIO pins also have specialist jobs as well as their general purpose one, but we'll just concentrate on the broader uses. These various types of connectivity can be broken down into different communications methods. A universal asynchronous receiver transmitter called a UART, a special peripheral interface called an SPI, inter-integrated circuits called I2C or I2C, and pulse-coded modulation called PCM. A UART employs an asynchronous serial communication protocol, meaning that it takes bytes of data and transmits the individual bits in a sequential fashion. A UART is typically used to enable communications between a separate microcontroller, like an Arduino or a Raspberry Pi Pico, or to connect a serial console to the Pi from another PC so that you can control it remotely. Most Raspberry Pis have 2 UARTs, but the Raspberry Pi 4 has 6. Known as a 4-wire serial bus, SPI lets you attach multiple compatible devices to a single set of pins by acting in a master-slave relationship between the Raspberry Pi and the devices connected to it. As there are more wires, it can operate in full duplex mode, which makes it run faster and more flexibly. Typically, SPI is used to send data between microcontrollers and devices such as sensors. I2C pins allow for low-speed, two-wire communication with a variety of external devices such as screens, sensors, and analog-to-digital converters. Because I2C is a multi-drop bus, this means multiple devices can be connected to the same two pins. This is enabled by each device having its own unique address. PCM, or pulse code modulation, is a digital form of a sampled analog signal. On the Raspberry Pi, it's a form of digital audio output which can be understood by a digital to analog converter to play high quality sound. This is all really just scratching the surface of connection options to the GPIO header. Your takeaway should be that it provides a diverse, flexible connection point to interface between the Raspberry Pi and its environment.